Hello, hello. I am coming. I'm having board problem, not problems, challenges. I'm having a board challenge. Just give me 1 second. I can hear you, but I cannot see you. That's a lie, actually. Uh, I'll be right there if you can hear me. I am coming. I am coming. I am off. Okay, here we go. Okay. Okay. Hello, hello. Oh, hello, hello. Oh, I see you. Oh, many people. All right. Good afternoon. Yes, let's do this. Let us do this. Good afternoon. All right. Hello, Lila. Hello, Raymond. Hello, Mike. Hello, Sophia. Hello, Tania. Oh, they all. Oh, excellent. And then hello, Shen, Camille, Nico, Jadith, Mancha, Fatima, Harris. Hello to all of the, and I appreciate like there's like a resurgence of video on the last day. That's a nice statement. Anyway, I appreciate it. And the pictures. And hi, now I'm doing the chat very quickly. Hello, Nico. Good evening. Good evening. Yeah, it does feel like evening. Good evening, Danielle. Good afternoon, Jadith. Good afternoon, Luis. Hello, Mancha. I'm good, thank you. How are you? Well, we're good. It's all about you. How are you is really the question, isn't it? Really at this point. But thank you. Hi, Montserrat. Happy. Yes, thank you, Shen. Well said. Yes, yes, yes. Um, yes. Good afternoon, Camille. Okay. Oh, no, wait, there's more. Good afternoon, Joyce. Joyce usually shows video. I'm not being per often anyway, whatever. Okay. So yeah, yeah, yes, yes, Raymond. Right. I'm a little sad. I mean, yes. I mean, I'm just anyway. If any of you even has the even 1% sadness, that means we've all done our job. But you could also be really. But yes, this is the last class for real. Okay, which means I'm going to get going and say good afternoon, Harris. Ooh, sir, I got a sir. That's even better than doctor. Okay. I had to work harder at the doctor part. Good afternoon, Abdul. Actually, also, very quickly, not here, but when I used to teach in the South when anybody ever calls, I mean, this was a really long time ago, but if someone called me sir, and it was before anyway, in the South when I taught of the United States, I mean, if someone called me sir then, that generally meant they had just cheated on something. I don't think that's what it means here. But okay, and hi, direct chat person. Thank you for the hi. Also, really quick point, as long as I'm being a crazy person right now. So, well, okay, so it's the last class, like Raymond said. I am, largely as just as relieved as you, that we're about to get a break. Of course, we're still in the last push. The last class is a last push for me. It's my last opportunity, to make all this experience worth your while in a way, intellectually. Like that is my goal for today, to sort of at least give you a glimpse as to why I think all this material is worth it. Like honestly, that's like the goal for today's, of course, for me to help you be prepared for your final exam. But as we already discussed, half of your exam, is you're going to fix whatever issues came from your midterm, which you all now have back. Um, and then the other half is to try to say something about the most recent material, on any of the problems that you see in the Google. Again, whatever, I will try to adjust this before I post the exam, this Thursday or Friday evening, no later than Friday evening. But whatever, and tell me, you can text me or email me if I'm under the impression that in Google Classroom, there was the two parts of the old final exam there. I believe that's still there. You should reach out to me, tell me if you can't open either document or something like that. One of the documents is literally a true false document. I'm aware of that, and that's unusual for the class, but it's correct. So you should let me know if they're not there. Again, whatever's there, you're gonna you're gonna choose one of the problems that you see there as your final exam problem. Although let me slow down to clarify that what you can't do is choose, like one of those choices I know is a Doppler effect problem. You've already done the Doppler effect. You're not doing that twice. Okay. That's also a sign that in some sense you were more efficient with your material and I was this semester than sometimes in the past. Like, let me really slow down and say this clearly. Like Doppler effect, you've already covered whether you chose it on your midterm or not. Like that we've done. So you're not doing that again for your final, but any of the other, um, I'll just try to be clear in Google Classroom, but I hope that's clear. So the other problem that you're going to do for your final exam largely is the material for that is what I want to finish today going over, and hopefully in sort of a slightly broad English conceptual way so you can really like get it and get why we did this course. Um, and then for any further detail, okay, and for any further details or further practice or numerical, like look at past videos is all I can say. I mean, but I think you'll find that the other problems that are posted in Google Classroom, like one of them is a circuit problem, that is a fair option. We never talk about circuits in the lecture, but you've done it till the cows come home in the lab. So, right. So just again, obviously just text or email me if there's like any confusions, but I think all the other problems that are posted as options, all the other full problems, I mean, they have many parts and stuff, like you're capable of doing. Like electric field, we totally went. I I think you have all the knowledge you need. But any last bit of conceptual understanding or unification is what I'm here to do today. Oh, I'm looking in the chat. I'm sorry, I'm looking in the chat. Wait, 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 wait. Okay, I'm looking in the chat. This is all good. All right, hold on, hold on, hold on. And I'll slow down in a second too. I'm like jumping because it's the last class. Hold on. I know you said not Doppler effect because we can't do it even if we picked. Yes. Okay, this is a good question in the chat. Right. So let me slow down, but I'm glad you are paying attention to what I'm saying. Right. I'm saying yes. I am saying that even if on the midterm you didn't pick the Doppler effect problem as one of your two, which some of you did not, and that was totally fine. I'm saying still, I don't want you to be thinking about the Doppler effect directly on your final exam. Like even if you already didn't pick it, that's correct. I want to make sure that everybody on their final exam is addressing electric fields in some fashion or another, because that's like the last material of the course. And so yes, tell me if that's clear, but yes, that is what I'm saying. And then no, and thank you for the sorry to be late thing in the chat. That's fine. Wait. Oh, wait. Oh, oh, okay. I see in the direct chat. Thank you for the closing the loop. That direct chat. Oh, all right. Someone else is saying in the direct chat that for the true false thing, like you can't access it because the form is closed. Good point. I will fix that. I think I can fix it right now. If I can fix it right now super quickly, I will. I mean, I'm going to try. But if it doesn't, then just remind me later. Hang on a second. Um, and let me say also, once I get rolling here in a minute, with the last material, um, all right, I'll pause for a second. Let me just see if I can open this, the thing, and you'll confirm. But yes, this is the time. Like, I know I'm talking all jumpy as usual. Like in about 10, 15 minutes, all I'm going to do is talk about physics. And again, I'm going to try to be sort of big picture about it to put the whole physics story together for you. And I'm going to try. And and when I do, it will hopefully help you, maybe in particular with this true false thing that I'm about to open up. Uh, but what I'm trying to say is, August 20th. Okay. All right, I'm doing two things at once. Hold on. I'll open this. This form that I'm about to open up will be a choice. You could choose it as one of your two final exam problems. And yes, it's true, false. And there's no work to be shown. That is true. So for some of you, it might seem like the far less stressful choice to pick. I'm aware of that. Let me even warn you though, before I open it up, and I'm glad someone's reminding me to open it. Before I warn it up, it's hard. Okay. It's not meant to be a trick, but the way to do this true false um, document is to pay super close attention to what I say today. So it sort of, some of you, it for some of you, it would be the much easier option if you think big picture and you've like, and if you can assimilate a lot of material in a short amount of time, like in a way I'm going to give you today. For some of if it feels like I land the plane of this class for you today, and you like really get it in nuanced physical terms, then the true false document is an easy way for you to give yourself a lot less work on the final exam. That is like definite, and you'll see that. Uh, and I'll say one more. On the other hand, I don't want to trick anybody. I don't want to fool you. The true false document is a true false document because like the actual things it's asking are very weird. I mean, not weird, like they're hard, they're abstract. And they are tricky. They're not designed to be extra tricky. They just like the physics just is tricky. So I want to warn you, don't choose the true false document just because you think, oh, like I don't have to show work, so it's like easier. Like it's very easy to get it very wrong if you just guess it and stuff and you don't know what you're doing, like and then there's no room to show your work and get partial credit. Like it for some people, it's a disaster. I'm just saying you have to make a mindful choice of whether this true false document works for you or not. And so, yes, I'm going to open it right now and I'm going to go a step further. I mean, I'm glad someone's reminding me. What you absolutely should do is sort of have it in front of you when I start talking about physics, for the next hour, 45 minutes, like try to follow along with my physics with what I'm saying, and in principle I'll be giving you answers to this true false document, like without saying that. You could sort of figure out the document like while I'm talking, and if it makes sense to you and you're like, oh yeah, that's right here, oh that's this question, then quark plus America, and feel free to share your answers with other people, but I'm not going to give the answers directly. Okay. And it is subtle and confusing. Should you, okay. So sure, I'm going to open this thing right now, or I'm going to try, and then sure, have it in front of you while I'm talking. And if it all seems to lock together, great. But if it doesn't, then do another choice and show all your work and give yourself the cushion of lots of partial credit. Okay. I hope that makes sense. All right. Let me just try to open it right now. And also, just like anything else, I may tweak this slightly. Like this is the old version. Like I'm not promising that I won't. I might add the word not or something to various questions so that the answer literally flips from true to false or false. Like you'll have to be careful about it. Don't you get my point? But all right. So hold on. Let me try to open it. You'll tell me if it does open. Okay. It should. All right. Tell me. I'm going to refresh my. I think I just reopened it. But again, if I just reopened it and you confirm, I'm not seeing the Zoom yet. I'll see you in a second. If you confirm that it's open and you can read it at all, great. Don't submit this one. Obviously, this is like an old, this is just for practice. Don't submit it. It'll confuse me. But just tell me if, um, can you read it? Wait. Oh, okay. So direct chat person or anybody, can you now access the
It still says not no
oh
longer
it
accepting
does.
responses.
All right. So maybe I have to make a new link. Hang on one second. Thank you. All right, hang on. Hang on. Um uh, okay, so refresh on you. So I literally it's a totally new link now that just got re-uploaded to your final exam or the draft final exam portal. So please, refresh on your side. Take note, it should look like literally a different link, a different URL. Uh, and then hit it and see. Oh,
Yeah,
oh,
it's working now.
Yes. All right. Thank you. Well, I totally good use
Thanks,
of time,
Professor.
guys. No, thank you both. Thank you all for like bringing it. If this class got shut down right now, that was totally useful. Wait. Oh, okay. Oh no, and I see where Mike, but I'm assuming that what Mike has in the chat is like now moot. I mean, it seems like at least one person is verified. So if Mike, if you refresh and stuff, it should now. Okay. I mean, at least at least it's working for one person. Okay. So it's 3:25. All right. Again, in a second, I'm gonna get to let me say a couple other things. Again, if there's anything unclear, text or email me, whatever. I'm a little bit, as always, on the last class, I'm always like a little bit of a freak, particularly though, just historically, I'm a freak on the last class of this class because this material is very near and dear to my heart. Like, I mean, in a different way, so is the material of Physics 203. For real, that's near and dear to my heart too. But then in some ways, the material from 203 is like all like the foundation, like duh, for the material here. And the material here, like, or at least the ending of the material here is like, I mean, it's like what I live for in some weird way. And I hope to get that across to you by the end. And of course, with your class, with 204, for me, it does get a little sentimental because I won't see you again next semester in any direct way. So I do before I start, but then it's weird because I always am desperate to get out like the last physics to you on this last day. So it's like a little bit of a weird balancing act where I kind of just want to say goodbye and thank you to you people, but I also want to like ram final physics down your notebooks. Um, so please forgive that strange tension. So we're going to end with physics. Like once I start saying stuff about physics, you can have that true false thing in front of you, or you can have any of the other documents in front of you, and you can be thinking in terms of your final exam. But I'm asking also for you to reserve a little space in your brain for just like there's like why any of this like might matter in life, or if you certainly if you're going on in science, which I hope in any way, graduate school, jobs, it may what you do may not directly relate to physics, but as of course physics does underlie like everything we do. So maybe, trust, especially if you've now gotten your midterm back and all that, trust that maybe things are kind of going to work out okay in this class for you academically. And if not, if you're worried about that, you could talk to me personally. And so 10% of your brain reserved for the non-academic part of this, and just like the why does physics matter at all anyway part of your brain. On that too, again, please don't be a stranger. If you want a letter or any way I can support your future or touch base with you again or find out how it's going in your future, I would love to stay in touch that way. Also, highly recommend, depending on where you're on the program, please apply to be a lab. If you apply to be a lab tech at any time, I mean, particularly being a physics lab tech, but it doesn't matter. If you apply to be a lab tech or work for the MSRC, I highly encourage you to let me know that you're doing that. Uh, because I can help like very directly with those applications. I mean, very directly. It's to our mutual benefit. If you try to become a lab tech, you should let me know. I'll just leave it at that. I know people, you know what I'm saying? Um, and MSRC, like it's only to, I mean, anyway, you get it. So there's that. Um, okay, so last thing before I get rolling with the physics. I'm looking at sorry, I'm looking at the chat. Oh, am I teaching next semester? That's a very nice question. So uh, to be totally blunt, right now I'm definitely slated to teach. I always teach. I usually every spring I teach 204. I teach all the 204s, particularly one that meets live. I mean, in person for 2.5 hours every Tuesday morning, where right now Macaulay meets. So I'm slated to teach. Yes. Now I'm not. Now, of course, I wouldn't be teaching you guys because you're done. We used to have a next physics course. We don't right now. Anyway, but as long as you're asking, there's a small chance that I might pull out. I mean, this medical stuff has been catching up with me recently, and I may have made a mistake. I might have been over ambitious trying to work it. So there's a small chance that I may just kind of medically crap, not that I may have to take leave and just recuperate from all this. But that's a small chance. Right now, I'm slated to teach. And if the next two chemos go fine, like, so, but thank you for asking. But yeah, I'll be around. I mean, I'll be around if that's. Uh, okay. Wait, it was, oh, and if there's any other questions, this is definitely the time. Again, I'm about to get to the physics. One other thing too, though, to be totally blunt or totally, hopefully, like re-encouraging. Oh, okay. First of all, again, I can't remember if I mentioned this on Monday, but grades, grades are due from the faculty to CUNY first, 11 p.m. December 27th. Like sometimes that gets extended, but my understanding, but I don't assume that. So right now they're due 11 p.m. December 27th. What that should mean is that you should get a spreadsheet from me probably 24 hours before then, or if I'm really on look, I try to get this all done before Christmas too. So it might be a couple days before then, but I think what I'm really asking is in the period like up to Christmas, um, I scrambled to get all these exams done and all these grades and stuff. So that is a period where I kind of need to deal with the whole group, not with individuals. And I cannot be late with grades. I will be to the last minute with grades, but I will not be late with them. And I cannot submit any grades until I have all the grades. You may know, I don't know if you know that or not, but all the grades have to get submitted as a block by 11 p.m. December 27th. So it kind of means like between the 20th and the 25th, I just need to do all of this. Um, but you will get a spreadsheet from me either the 26th or a couple days before with the full calculation of your grade. Like if you're concerned about that, you'll see how all the numbers work together and that it is a math formula, even though it's designed to be to your benefit. Like you'll see the system and you'll see that it's the same for everybody and all that stuff. And you'll see where your grade came from. And hopefully it's a good grade. But you will get a spreadsheet before they get submitted. So at that time, then if you don't understand it or you have issues, you can reach out to me. And there's like a little time in there before it goes official. Okay. But I guess what I'm saying is bear with me and wait for the spreadsheet. Um, and okay, if that makes sense. And so at latest, that spreadsheet will come like at night on December 26th. Okay. Okay. Again, if that's not clear, let me know. So all that said, yeah. Oh, that's a really good question. So someone just asked in the chat, like, so do you get your, maybe that's even why I'm saying this. Someone just asked, do you get your final exams back like before that spreadsheet or not? Not necessarily before. You will get your final exam back. Like you won't just get a number. You will get it back. It won't have a lot of like, here's how you can improve on it. It won't have super detailed feedback of what to do next because there's no next. But it will have all the justifications of why all the points were removed, if points were removed. Or if it's the multiple choice, or if it's a true false, you'll know what you got wrong and what you got right. You will get that back. But yes, in many cases, you're going to get that back like in the same instant that you get the spreadsheet. So there's time. There'll be like a day where you can make sure you understand what happened and where you can, if you think I made a mistake, you can politely point that out or ask me about it. But yeah, it may be simultaneous. You might get your final exam at the same moment that you get the whole spreadsheet. So last thing on that too, if there's an issue, look, I am not perfect, obviously, and neither are some of you. When you get the spreadsheet, if you think there's an issue with your grade, like if you don't understand how I did it or something, politely ask the question. Like that's a key moment. If you're thrown by your grade, the bet there, I'm telling, and most of you won't be, but I am telling you right now, of course things happen. And sometimes you misunderstand it, sometimes I miss it or whatever. It, the re, if you are thrown and concerned, the reason that there's a 24-hour period for you to raise it to my attention is like, yes, it's a possibility that I just missed something or you turned in something and I didn't realize it or whatever, whatever. But I plead with you, your best strategy at that moment is to ask like as respectfully as possible. Like don't lean in with anger or fear. just lean in with inquiry. And I'm there. I am telling you, I change things. Like I make mistakes and I know it. I'm perfectly happy for someone to put, and I want your grades to be good. So if someone says, wait, professor, like with all due respect, I think maybe you don't realize that I did turn this thing in or like whatever, I will totally look into it and I will hope as much as you that you are right and I am wrong. I do not mind saying I'm wrong in that instance. But my chance of doing that is much higher if you just lean in like we're working on this together, right? Like I'm asking a question. I'm not making an accusation or like setting your barn on fire, right? I mean, you all follow that. And I think you're all that kind of person anyway. So if there's an issue, just ask and I will look into it and I will root as much as you for me being wrong. And then I will change it, right? And I'll communicate with you. But just like leave it on that level. Not that like anger just breeds more anger. Okay. And I understand all anger comes from fear in both of our directions. So let's just not be afraid. Let's just, okay. But yeah. Okay. Cool. Okay. So we're almost, wait, this, I keep thinking, so we have, okay. Last thing, since I'm talking about grades and all this, and of course, that's like largely what's on your mind. I mean, it only took me like 25 years of teaching to realize that, of course, people care more about grades than physics at this point of the year. Like, duh. Um, I used to not realize that though. So in terms of grades, I also want to say this whole system where I'm saying you are going to redo half your midterm as half of your final. I also just want to point out, to be really honest, that is largely because I think it's a good thing for your efforts not to be wasted and for you to like, yeah, and for your efforts not to be wasted. And because I feel bad that it took you so long to get your midterm back that I want to have you have an opportunity for it not to have just been, an irretrievable shock or something. So that's why I'm doing that. But that said, and I'm doing it in all my classes this semester, but just so you know, most of you actually did very well on that midterm. I don't want you to think that I think you screwed it up. Like actually, you guys rocked, most of you like did very well on the midterm. And so my point is not that there's like a huge issue that needs to be recalibrated here. I think there was in my other classes, which is when I made the decision. I mean, in the 203 classes, just to be clear. But your midterms were good. In fact, I think maybe in some cases I should have, whatever, it doesn't matter. Your midterms were good. So don't this thing that we're doing is not because I think you're in trouble or something like that, so that you know. Um, I would say the biggest issue in the midterm, besides, mentioned yesterday that if you chose the oscillating problem, you really have to lean in more. You really have to like explain more why omega is the square root of the constant in the differential equation, which means you have to like show me that you take two derivatives, yada, yada. And some of you did, so you could show the others how to do that. But I'll also say on the Doppler effect problem, and hopefully I will get to this directly in the physics context in a minute on the Doppler effect problem, on the last question of the Doppler effect, most of you, to my mind, kind of didn't explain that enough. I am hopefully going to get to a point today where I give you, with my words, a better example of what I think is the explanation there. But in case I don't, there's definitely old videos to watch. Just watch me go where any video that says Doppler 4 cases or 2 cases of anything that compares the cases of the Doppler effect in my old videos, scroll or scrub to the end of one of those things, and you'll see me make a very big deal of what it means, not just that the receiver and the source get two different frequencies in a Doppler effect. Like, yes, that is the Doppler effect, that the source and the receiver measure two different frequencies. Yes, like that is the Doppler effect. But something that's very subtle about the Doppler effect that your math shows, if you do the math correctly, is it's not just that the source and the receiver get two different frequency measurements. It's that the way in which their frequency measurements differs depending on whether it's the source moving relative to the medium or the receiver moving relative to the medium. Like that you don't get in the examples of those numbers on your exam, the source measurement of frequency is 256 hertz. It's the Doppler effect that the receiver will not get 256 hertz. Like that is the Doppler effect, that the receiver will not measure 256 hertz. But if you look closely at your numbers, you notice that what the receiver gets when the source is moving is different from what the receiver gets when the receiver is moving relative to the medium. And if you really stand back and think about that, that's weird because everything that you're using to solve the Doppler effect is relativity. And according to relativity, me moving toward you should be the same effect as you moving toward me if all the numbers are the same. All right, I'm speaking fast, but think about that for a minute. So, two things. One, at the beginning of your Doppler effect problem, if you did it, I may have taken off 2 points. Even if you have a bunch of relativity things written down, I may have taken off 2 points to say, like, no, but you need to explain this. Like, how is this actually like related to your work that you're all about to do? Okay, so think about that and elaborate on that. But then, second, if you're really believing that you're using relativity to do the Doppler effect, then I would think relativity would say whether I move toward you or you move toward me, we should get the same effect in the universe in the same numbers. But we don't. So something is happening that's very deep in the Doppler effect. That's what I want to hear about at the end. And in short, so I'm going to use this as a segue back to physics. What's happening is it's not about whether the source is moving to the receiver or the receiver is moving to the source. Like if that's all there was, source and receiver, then whether one was moving or the other, then relativity would say we'd get the same answers. It's the relationship between the source and the medium versus the relationship between the receiver and the medium that is what's going on. In other words, the medium is playing a crucial role in the numbers. And that's what I want. Okay, so that's a lot. So just think about that. That if I took off 2 points at the end of your Doppler effect, it's only 2 points, obviously, but that's what I'm getting at. And that is also ultimately tied into what I now want to, you know, physically analyze for you in this last class for the next 40 minutes, which is plenty of time. So I don't know if that helps at all, but I know it's only about two, but that's what many of you don't have to do that much to redo your problem from the midterm, but you do have to redo it from scratch. Like if you got it all right, just make it even more beautiful. And more, like if you know you got it all right, then now be proud of yourself and be like, here is a freaking poster presentation of physics. Like I could submit this to Prism or whatever. Like really, if you got it right, just now know you get your physics so dazzle me. But if you lost points at the end of the Doppler effect or the beginning of the Doppler effect, it's probably because of what I just said. So really think about that and try to see how it's connected to what I'm about to talk about with fields. Okay, I'm looking at the chat. Sorry. Oh, yes. Sorry. Okay, yes. Nico in the chat. Sorry. Absolutely, Nico. I did say that, and I will hold myself to that. Wait. Uh, Yes. So Nico said, again, I honestly, I don't even think your class needs this that much. I may be in the way, maybe the grades are going to be, but yes, I'm agreeing. Whichever of your two exams is a higher score out of 100 will weigh more in your average than the lower of your two exams. They will still both count. But yes, I mean, yes, to be clear, like Nico is confirming, uh, I will count your higher score more. Yes. Um, okay. Okay. So let me just. So are we? So we've got like 20 minutes, 40 minutes, 38. Can I take a breath? Are we good? Like, is everybody clear on? Great. Okay. And again, I believe it says in Google Classroom, I have till Friday evening of this week to like clearly post a portal and a document for you to put your final exam stuff in. But you pretty much know what's going to be in there already. And I might do it earlier, but I have till Friday evening to do that. And then you have till Wednesday evening, midnight to send it back to me, right? So are we all clear, like how the ship is getting, how the shop is getting closed down? Like, can I do physics? Like, honestly, are we good? Yes. Okay. Thank you, Abdul. Thank you, Abdul. All right. Abdul. Um, okay. Okay. So here we go. All right. Oh, great. Oh, thank you, Montserrat. Thank you. Okay. Um, okay. First of all, I'm now going to recall or summarize what in principle was our last conclusion from last week. And it's a conclusion that definitely one of the problems in the final is like about, okay? The law is Gauss's law. What it is saying in English, and I'm going to just like talk now, so I would definitely recommend taking notes or whatever, but I'm not going to write all this down. Um, I mean, I'm not going to write it down myself. Oh my God, sorry. Also, notice the portal for tonight, the game portal, is worth like 30 points or something. Notice the instructions for the first and last time in the semester. If you submit the portal, the game turned by midnight, don't just say, for one time, don't just say I said hello. Write something that you learned from today, something that makes sense for you for today, for what I'm about to explain, just even one sentence. And you'll get 30 points. I think it's 30 points instead of five. Okay. It's just another opportunity to like focus for one last time. So, okay. So, what Gauss's law is saying in English is that through any closed surface, anywhere in the universe, anywhere in a lab, in outer space, if you imagine a closed two-dimensional region of space, a closed surface, which really means a container, right? So if you imagine the surface area of a globe, the rind of an orange, or you imagine like a cylinder as is drawn here, like the walls and caps of a tennis ball can container or a Pringles potato chip container, right? If you imagine a surface that is closed onto itself so that it constitutes a container, if you imagine any closed surface anywhere in the universe, the net flux, the net electrostatic flux emerging from that container is necessarily fully determined by the amount, the magnitude of source charge enclosed within that container. So, okay, so the left, I'm going to say that again in a second, and I'm certainly going to say what it means and why. But let me say it again. Like the left side of this equation is electrostatic flux through a closed surface. The integral is double, just to emphasize it's a two-dimensional integral. Like ds, the independent variable, is surface. Like so each infinitesimal tile of surface is what we're examining and adding all up and asking how much electric field or how many electric field lines are going through those bits of surface. So if you add up all of these surfaces, right? Again, that's why it's a double integral. It's just double just because it's two-dimensional, right? If you take all of, if you add up or account for all of the electric field going through a full surface of space, like they're like a full two-dimensional region of any space that you're analyzing. And if you restrict yourself, if you specify that the surface you're looking at is a closed surface, so that's the circle on the integral. If you look at any surface in space that is closed in on itself so that it constitutes a container means there's a definite inside and a definite outside, and you can tell the difference, right? What's inside any container is a definite, unique volume, a three-dimensional space, right? Well, what the right side is saying is if you count up all of the source charges or all the source charge in that unique volume, if you look at all the charge enclosed by the enclosure, by the closed surface, then the total amount of that charge will fully determine the total amount of flux of field lines busting out through the container. And the equal symbol means it's literally the answer you'll get for flux will literally equal the total amount of charge divided by this universal constant E naught, which is a constant and which seems like arbitrary. I mean, it's just a number, right? I mean, and it just makes the units work out and all that. And it doesn't seem right now there's any significance to the number. It's just the number that needs to scale things so that we stay in the MKS system of units. Okay, so sorry. So, what is this saying in English? And I encourage you to write the following down. What it's saying in English, it's saying that electrostatic flux through the boundary of a container is fully determined by the stuff, the charge within the container. Okay. That's what it's saying. Again, that doesn't tell you why I care necessarily, but that's what it's saying. Uh, but let's be clear, in terms of why we care. It what it's saying is, as opposed to the following, it's saying that the net electrostatic flux out of a container is independent, is not at all affected by the following four things. Please write these down. Like the flux out of any closed surface, any container, is independent of number one, the size of the container, the size of the closed surface. It doesn't matter how big the closed surface is. And that's what we found last week when we looked at just a sphere as an example. You make the sphere bigger, well, you have a bigger area now, so you'd think you'd get more flux. Remember, flux is stuff through an area. What kind of stuff? Electric field strength. So last week we said we analyzed this for a sphere. We found even if you make the sphere bigger, you'd think you are getting more area. So you'd think you'd get more flux, but you're getting weaker field when you make the sphere bigger. Field lines spread out, right? They get less and less dense from a point. And we found they spread out at exactly the same rate as the area, the surface area of a sphere increases. The field strength gets weaker by R squared. Surface area of a sphere gets bigger by R squared. And it's not a coincidence. So the field weakens by it spreads out at exactly the same rate as a sphere spreads out. So we found out that number one, flux through a closed surface is independent of size of that surface. But number two, once we generalize all of this, so number one, independent of size of surface. Number two, it's independent of shape. It doesn't even matter if it's a sphere or not, for reasons I'll remind you in a moment. But it doesn't even right. That's why here I'm intentionally trying to draw a cylinder to show the law is still true. It doesn't matter what the shape is. So that's number two. Number three, doesn't matter any charge that's outside your surface. Like there could be charges over here. There could be a bunch of source charges everywhere. And of course, there are everywhere else in the universe. You're just examining this little area over here. And what we're saying is no matter what's going on everywhere else, that's not going to affect the flux through the area that you're looking at. Well, oh my God, like that is super powerful, empowering, and helpful. That if you just want to look at an area here and ask the flux, all you have to do is look at the charge within that container. And even though there's charges everywhere else in the universe, you don't have to care about them at all. You don't. Why? The simple answer is even if there's a source charge over here and it's of course sending field lines everywhere, any field line that it sends into your container, you would think would affect your flux, but then it's going to come out of your container somewhere else because field lines are never created nor destroyed in random moments in space. So, right? So any flux that would come in would go out from anything outside. So, third factor is you don't have to. The third independence is that the total flux through a closed surface is independent of any charges not enclosed by that surface. So that's number three. And number four is the actual shape or distribution of the source charge itself does not affect the total flux through the closed surface. In other words, again, look at the example I'm drawing here. Like what we analyzed on last week, we sort of did all this analysis for the very simple case of a dot inside a sphere. That's like the most simple one to analyze. But now I'm generalizing and saying whatever we found, whatever math we did or thoughts we did for the simple case of a dot within a sphere actually even if the situation's more complicated than that, even if you don't just have one dot, if you have a bunch of dots, and even if they're, say, arranged, for example, in a line, right? So that what you want to surround the line with is not even a sphere, but like a cylinder, for example, right? Apparently, this law is still true. I don't need to know that the dots are arranged in a line or if they could be arranged in a cow or amoeba shape. It doesn't matter how many dots there are or how they're arranged. It just matters what the total charge is that is inside the container. Okay, so very quickly again, I'm saying the implication of Gauss's law is that if you want to know the net electrostatic flux, the total impact of field throughout some closed surface in space, all you need to know is the amount of charge inside that closed surface. You don't need to know how big the surface is, what shape the surface is, about anything about charges outside the surface, or about how the charges inside the surface are even arranged. All you got to know is the magnitude of the charge inside the surface. Now, that itself is part of the reason that we care about flux. Like, I know if you're flux, we just started learning about field, and then suddenly we're talking about flux. And it seems like very abstract and very obscure, maybe to some of you, certainly did to me at first. Like, what is flux? Like, stuff through an area? Like, why? Okay, why we care about it in part is because it makes our life so simple in the way that I just described. Like, again, please remember the first time we ever did a integral of a dot product of something was when we moved from analyzing forces to analyzing the path integral, like the integral of the dot product of force with dx, with one-dimensional space, right? We did, I mean, that's in theory, that's like earlier physics. But when we learn Newton's laws and free body diagrams and all that stuff, that is such a powerful way of understanding the world that in principle, it's complete. If you know all the forces acting on a point of mass at a point in time, at a point in space, if you know all the forces acting on that point, like according to a free body diagram you draw, then you know the instantaneous acceleration of that point mass at that point in space, at that point in time. And from that, in principle, you can predict its future velocities, its past, or retrodict its past velocities, and you could find out where that particle is going to be at any given future moment in time. Or you can solve crimes and figure out where the particle was at any past moment in time. In principle, part of the power of Newton's laws is not just that it's like sort of cool and convenient. It's the whole picture of the universe in a way. It is. You don't need any more physics in a way, classically, than Newton's laws because of the assumption that Newton's law says as long as you know everything that's going on at one frame at a time, then if you analyze a frame of the movie of life comprehensively enough, then you can extrapolate all the future and past frames, and you have the movie of life or the movie of space, time, and matter, right? And that's all you need. If you're willing to analyze the universe pixel by pixel, all you need in mechanics is Newton's laws and forces, and all you need in electricity, if you now you're microscopic level of electrons and protons and whatnot, all you would need is to know the electric field produced by every single point of charge at every single point in space at every single point in time, i.e., in the same way that all we would need is free body diagrams to do mechanics, all you would need in electricity is your ability to solve one of those final exam problems, the one where we have two point sources and you add up the vectors and you get the field at the origin, like we did that once in class, and that's one of the final exams. Now, it's like a lot of computation, but it works to get the field from two source charges. So if that's all we ever had in life, that's all we would need is forces and fields. But in mechanics, we decide to start integrating forces through space so that we can analyze finite regions of space that are made of continuous, infinitely indivisible constituent parts, right? We decide to start integrating force throughout space and analyzing this thing called work. Even though we don't technically need it, we do it to make our life much more powerful and robust and easy. We start integrating force over space so that we can say, oh, work transfers energy, and we find this quantity called energy, which remains constant from one situation to the next, even when velocities are changing and positions are changing, energy remains the same. So when we're looking at regions of space in mechanics, it's a lot easier and more powerful ultimately to think in terms of this constant quantity called energy. And so we do. Same thing here in a way. The reason we care about flux is we don't want to just look at life in a pixel by pixel manner. Excuse me. Forces and fields allow us to look at the universe one pixel at a time. If ever you want to analyze a bunch of pixels that are continuously attached with one another, if you want to look at a finite region of space or time at once, then we integrate and do dot product. And in electricity, the result is this thing called flux. And flux remains constant for situations, even when a whole bunch of other factors, the four that I just listed, are changing. Okay. So, on the one hand, the reason we care about flux is exactly that flux is to electricity in a way as energy is to forces in a way. I mean, that's a loose analogy, but it's a quantity that remains constant even while a bunch of other things vary. So we can use it to solve problems involving the electric field. Okay. So part, I don't know if that helps or not, but that's one picture of Gauss's law. But now let me go on. Uh, hopefully you were able to write that, whatever, but okay. But what is, I mean, in a way I've already said, but now like, what does it really say? Okay. Oh, wait, I'm looking at the chat. Great question, Jerry. Wait. Great question, Jerry. I mean, he said, does this hold for only a single charge enclosed or multiple different charges enclosed? So the answer is multiple. Like, I'm glad you asked, but that's my number four factor when I said it was independent of four factors. And the last one, I think it was the last one, was the distribution of charge within. Yes, I'm saying you could have a million charges within the container. You could have a million different dots, a million different point sources, or even more exotically, you could have so many point sources inside the container that they're all attached together and make a shape, like this picture here, like a line of charge, or you could have a plate of charge, or you could have a cow of charge. Like, I'm definitely saying, like, it's a great question because that's a really important point. I'm saying all you can have as many charges as you want arranged however you want inside the container, and all that you need to know is the total amount of coulombs of charge that you have. That will determine the total flux coming out of the container. That is totally what I'm saying. And so hopefully that answers. But now here's why, or here's why I care. Both. Because remember so first of all, remember, flux is field strength times area. When we're drawing field lines, as I've drawn here, when we're talking about field lines, remember, it's field lines are not vectors. They're lines. They can curve, they can bend, they don't end except at negatives, and they don't start except at positives, right? They just go on forever. So they don't have length. Remember with field lines, it's the number of field lines per unit area on the page, like the density of field lines that indicates field strength. And it doesn't just indicate it in a rough way. Like once you pick your scaling factor for drawing field lines, then literally, if you count the number of field lines in a picture and you multiply by your scaling factor, you know exactly what the field strength and what the newtons per coulomb is, right? Right. So number of field lines per area on the page indicates strength of field, like literally represents numerically, precisely, strength of field measured in newtons per coulomb. That's field strength. And flux is field strength times area. So in English, flux, field strength times area, means number of field lines per area times area. So after all of these detailed math things, the real reason we care about flux in a way, the real reason we care about flux is because it's such a simple thing to see and count and measure on a diagram. Flux is number of field lines per area times area. So the areas cancel. I'm not kidding. And flux just means number of lines. When you're so literally, when I'm talking about the flux through an area, I'm just literally talking about how many lines went through that area. So if you have some bunch of charge, like here in this picture, a line of charge, right? And yeah, you have a line of charge. And you want to know how much flux it's producing through some shape that encloses it. The reason, so I'm saying in this case, so if I drew it a little bit more accurately, like in this case, the flux would be, 8 lines. That's the flux, 8 lines. And then I multiply by the scaling factor, so I get 8 re-expressed in terms of like newtons per coulomb times meter squared. But the flux in this picture would be literally like, what is flux? It's the number of lines I see coming out of the surface. In this case, 8 lines. Now, if you really think of flux as just number of lines, which I'm telling you, you can and should, it's not an approximation, it's an exact truth. If flux just means number of lines, then what Gauss's law is really saying is, well, yeah, okay, like duh. Like the only thing that can ever create lines in the first place is positive source charges. And the only thing that can destroy lines or terminate lines is negative source charges. So of course, if this picture is producing 8 lines, if I reimagined and drew like a cube around that line of charge, a cube of a much bigger size, if I do some other shape of some other size around that line of charge, like it still would only be able to capture 8 lines because that line of 8 field lines, because that line of charge only created 8 field lines, and field lines are not created nor destroyed on the page, right? So in a way, here's where I'm going with it. I don't know if that makes sense or not, but I'll just say one more. I'm saying if you think of flux as number of field lines, which is what it is, then in some ways it makes total sense that the total number of field lines coming out of a container could only be determined by the amount of stuff inside the container creating those lines. Nothing else could affect the number of lines that you grab with a container. It wouldn't matter what kind of container you pick, and it wouldn't matter any other dots that are outside the container. All that would matter is the dots of charge inside the container creating the lines, right? So in a way, what I'm saying, what Gauss's law is saying, and you'll know you understand what I'm about. If what I'm about to say suddenly strikes you as like, well, duh, is that all you're saying? If you feel that even for a moment, then you're with me. But then let me show you why it's not a duh. In a way, we're saying, look, it's just like, I'll even write this down. And by the way, I hope I answered Jerry's question. Maybe Jerry in the chat will probably just let me know if I did answer the question. But um, I'm saying this. I know we have 10 minutes left, and the plane's almost landed in a way. I'm saying, look, forget field and all this abstraction. Just think of a sprinkler of water, like a sprinkler. So it's sending out jets of water. If you imagine yourself like the sprinkler's going like this, and you take a big tent or a tarp or something, and you close and you put the sprinkler in the big tent or the tarp. So now water's like slamming on the inside of the tent or the tarp, and you give yourself a minute, and after the minute, count up all the drops of water somehow. You measure all the water that's accumulated on the inside of that tarp or tent, right? The amount of total, which would be equivalent to like having electric field lines coming out of a source charge and then asking what's the total amount of field lines like slamming through some imaginary container of space, right? If you do this in reality with water in your mind, and you just ask how much total water is accumulated through the closed surface of some tent or tarp, the total amount of water you're going to get accumulated is not in any way going to be affected if you change the shape of the tent, right? And it's not going to be affected if you change the size of the tent. It won't freaking matter. The water that you accumulate on the inside of the tent will just fully be determined by how many drops of water came out of the freaking sprinkler every minute. Right? Like, duh, because water does not spontaneously generate itself or disappear along the way from the sprinkler to the tarp. Whatever is created by the sprinkler is what you'll get in the tarp. Oh, great. Okay. Okay. Great. And thank you, Nick. Okay. I'm going to totally run with Nico's comment here. Okay. So here's the depth of of almost the whole point of all of this. If you see that analogy, like Nico, if you see that all the Gauss's law is saying in a way, I mean, it's a very important, powerful computation tool. It allows us to compute like a lot about electric fields for the rest of our lives. But if you but if you see that what it's saying is the total amount of field accumulated in a container or passing through a container is fully determined by the source charges inside the container creating those field lines. If you see that all it's saying is like field lines act like water, then you get it, first of all. Okay, so good, Nico and anybody else. Then you get it. That's all Gauss's law is saying, is that the total amount of field lines crossing through any container is not determined by the nature of container. It's only determined by the nature of what's contained, the source charges. Okay, so if you get that, great. And then if you're thinking, well, if that's all it's saying, like, why do we have to talk about this for like 2 months? Like, Jesus, well, duh. Here's why. We're saying it all makes total sense if and only if field lines act like stuff. If field lines act like water, fine. But field lines totally are not water. Field lines are not stuff. Water is a thingy thing. Of course, thingy things are not created nor destroyed spontaneously in space. And of course, thingy things are conserved. If you start with five of them, you end with five, whatever. That, but field lines are just raw information. These field lines that we're drawing and believing in following these rules, these field lines represent newtons per coulomb. They represent the data, the numbers describing how strong these protons are here and where they are. These field lines, like whether you think of them as vectors or you think of them as lines, and you think of all these analogies, yes, we're trying to get you to visualize them more and more, just like concrete objects, so that we can make predictions in our mind and deal with them and all of that. But at their base, these field lines are unthingy things. They are just bits of raw information in the universe that we believe must be in the universe. Otherwise, a proton over here could not affect an electron over here in the precise, predictable numeric way that it does, right? So the field lines are the representation of the info, the numbers and directions describing protons over here to bits of space over there. This raw information, we're saying, obeys Gauss's law, and we're saying Gauss's law is utterly obvious as long as you think of raw information the same way you would just think of drops of water. But then what we're saying is, holy crap, that means bits of raw information act like water. Like what? Do you see what I'm saying? It's a perfect analogy, and you should hold on to it. I mean, like Nico and others should hold on to it. But I'm saying now, hold on to the implications of that. What we're finding is that unthingy things in the universe, raw bits of information, whether you want to think of them as numerals or vector arrows or field line, like raw information in space over here that's telling a bit of space over here, what's going on over there? The raw information sits in space and acts just like actual material objects do. That is a big implication. It's part of why I believe in fields, because they actually act like stuff. That's now we have 4 minutes. There's actually 4 minutes to go on this. But that is big point number one. Why do you care about Gauss? Why do I care about Gauss's law? Because it's a strong indication that the immaterial fabric of the universe is functions in the way that the material fabric of the universe does. It means I believe in unthingy things. Quite frankly, if I could get this out in 4 minutes, you'll see in the end of the day, I actually believe and you know this, 99.999% of each one of you is empty space. I mean, you know that from chemistry and all of every atom is empty space, right? And you are made of atoms. Mostly what's going on in the universe is empty space with huge amounts of information in it in the nature of fields. We are here thinking we're studying stuff in space and time. We're really, as scientists and as human beings, studying what is going on in space and time between the stuff, the immaterial contents of space and time. In fact, in my understanding of physics, are in fact what's governing over all the interactions between the seemingly material things in space and time. Matter is but a blip in what's really going on in space and time. Now, I've got 3 minutes more. That's not a lot to summarize the crazy. Now, look, I may have answered some of the true false questions. I may not have. I don't know. That's up to you to decide. But here's the thing that I have to say last in 3 minutes is everything I just said is about fields and all that. And the field over here is the information over here of what's going on over there, right? That's what the field is. And I'm saying it acts like water. But the only question that remains is, but wait a minute, like what happens if something changes over there? What happens if the charge moves? What happens if that line of charge that I depicted in this picture is actually a current? So that the charge is actually flowing. Now that's a change. How does the change get updated in the universe? Like, how does the new information, the update to the old information, like travel from here to there? Great question. Now that's a whole course in itself. But the simple answer is, the fast answer is, well, number one, if you have a line of charge, if the charge is now all moving in a steady way, so it's all changing, but in a steady way, like constant velocity, that's called a current. And what current makes, it'll affect all of those lines, all those symmetric lines coming out. Those symmetric lines coming out will now fall into a different kind of symmetry, a symmetry that captures the fact that the dots aren't just sitting there, but they're flowing. They'll fall into lines that circle around the flow of charge. Remember, field lines are always only as asymmetric as the thing that causes them. So once charges are flowing in a line, the field lines fall into a new kind of flow. They wrap around. But what happened? And if that's it, then you just have this new field that we call a magnetic field. It's just a different shape of the old electric field, capturing the fact that now things are changing. But if the change, I'm going to say this, say the change is of the sort that is infinitely differentiable. Say the current that you make is not just a steady current or a linearly changing current, but like a cosinusoidal current, right? Okay, bear with me. If you have to go, go. I know it's 4:20. I could do this in 1 minute. I think it's worth it, but if you have to go, go. Let's say the current is changing in a way that has infinite number of derivatives, like a cosine current, right? Then the change produces a change, which produces a change. So you'll have lines that produce lines, which produce lines around them, which produce lines around them. And what happens to the electric field and the magnetic field if they are cosine functions? Then you take a couple of derivatives, and what happens is that the fields will propagate out in the manner of a wave. The fields will satisfy the wave equation, where the speed of the wave is that crazy constant that we use for electric fields times a crazy similar constant that we use for magnetic fields. Looks totally crazy, but if you do the math out, you find that the speed at which this wave propagates out is the speed of light. So what light is, I know I'm in the last minute here. I'm saying, bottom line, fields are unthingy things, raw information sitting in space. The way fields update, the way changes to the field move from one place in space to another, is it updates propagate according to the wave equation. The field will satisfy the wave equation with a speed that is the speed of light. So light is a unthingy wave traveling through a medium known as electric and magnetic fields. And that's already cool enough, I think. But if you remember that we only believed in waves in the first place, sound waves, because they traveled through mediums that were thingy, now we're saying at the end of the day, you can make a medium that is unthingy. You can have a field that's already raw information. And when waves propagate through that unthingy medium, you have unthingy waves traveling through an unthingy medium. Those unthingy waves traveling through an unthingy medium is what we experience as light. The speed of light is the rate at which the universe talks to itself. The speed of light is the rate at which one point in space communicates, updates to the raw information describing itself to any and all other points in space. The speed of light is the speed at which raw information propagates through a medium of raw information. That's the point of all this. You've been very, very, very patient. Don't be a stranger. Have a great final exam. I'm here to answer questions, but I'm stopping the recording. I've really enjoyed working with you, and I hope, and don't be a stranger.